All right, so in the previous section, or previous video rather, we talked about some mathematical models for differential equations. We talked about what a differential equation was, solutions to differential equations, and those sorts of things. I want to do some examples where we're using some of these ideas now. So for here, I want to verify that y equals 2x squared minus 1 is a solution to this differential equation, y prime plus 4xy equals 8x cubed. This is a first order differential equation. So to verify that this is the solution, what I would need to do is use y and y prime, which I'm going to have to find, and substitute them into the left-hand side of this equation to show that I end up with the right-hand side. So y prime for this function would just be 4x. Okay? So this implies that y prime plus 4xy is equal to 4x, that's my y prime, plus 4x times y, remember that's 2x squared minus 1. If I distribute that 4x in, I get 4x plus 4x times 2x squared is 8x cubed, and then I get minus 4x here. But this 4x and that minus 4x will cancel, giving me 8x cubed. And that's it. That verifies it because, again, all we were trying to do is show that when we find a solution, it satisfies this equation. It makes both sides work out to the same thing. Okay? Now, this differential equation actually has infinitely many solutions. This is just one of them. But more often than not, we're going to be looking first at a family of solutions or a family of functions, all of which satisfy that differential equation. So here's a different example. I want to show that the family y equals c1 e to the x plus c2 e to the 5x is a solution to this differential equation right here. Y double prime minus 6y prime plus 5y equals 0. So this is a second order differential equation, which means I need the first and second derivative of this. So I have y already. C1 and C2 are constant, so my y prime here is going to be C1 e to the x plus 5 C2 e to the 5x. That's what that derivative would look like. I also need y double prime. So taking the derivative of this, I get C1 e to the x plus 25 C2 e to the 5x. Hopefully you're comfortable enough with derivatives to know where I'm getting these from, okay? Now, I want to substitute y prime, and y double prime into this. So y double prime minus 6y prime plus 5y equals, I'm actually going to plug things in now. So y double prime was c1 e to the x plus 25 c2 e to the 5x. That's my y double prime. Next up, I have minus 6 y prime, which is this guy, c1 e to the x plus 5 c2 e to the 5x. Okay, plus 5y. So plus 5 times the original function, c1 e to the x plus c2 e to the 5x. Now let's distribute some things and see what happens. C1 e to the x plus 25 c2 e to the 5x minus, distributing a 6 in there, I'm going to get minus 6 c1 e to the x minus 30 c2 e to the 5x. Here, distributing that 5 in, I'm going to get 5 c1 e to the x plus 5 c2 e to the 5x. Now, I'm seeing some exponentials involving e to the 5x and other exponentials involving e to the x. So let's deal with those separately. I have c1 e to the x minus 6 c1 e to the x plus 5 c1 e to the x. They are the same terms but with different coefficients. So they're not really the same terms, but they're the same types of terms. So I have a coefficient of 1, negative 6, and 5, which adds up to 0. That means these three guys all add up to 0. Similarly, 25c2 e to the 5x minus 30c2 e to the 5x plus 5c2 e to the 5x. 25 and 5 make 30, which cancels with that negative 30. Everything goes to 0, which is what we were hoping to get. So what this tells me is that regardless of what c1 or c2 are equal to, as long as they're constants, that will always result in a function that satisfies this equation. Notice the c1 and the c2 didn't ultimately matter what they were equal to here. Okay, so that verifies that the entire family of functions forms a set of solutions to this dE right here. All right, last one. So typically, when we're using a differential equation, we end up with a family of solutions like that previous example. But in a particular model, if we're trying to model, something like population growth or the movement of a spring, like the two models we looked at here, we don't want infinitely many functions. We want a single function that models the actual phenomenon we're looking at. So what we have to do is find a way of taking that infinite family of solutions and narrowing it down to just the one that works for our purposes. And the key to doing that is using something called an initial condition. So basically, an initial condition is a value that the solution to a differential equation has on its curve. So in other words, it's a little extra information about the function we're talking about. Usually it's going to come in the form of y of t naught equals y naught. So in other words, we're going to know for some specific input what the output of the solution function would be. With that information and with a differential equation, we can oftentimes solve for just a single solution instead of an infinite family. One thing, however, that's worth mentioning is the higher the order of a differential equation, generally speaking, the more initial conditions you need. So you might need something of the form y of t naught equals y naught, but also y prime of t naught equals some other thing, and y double prime of it kind of depends on what the dE is to determine how many initial conditions you need. We're not getting into the nitty-gritty of that in this class. That's more of a topic for like a Math 420, which is like a full intro to dE class. So let's just do one example here where we have an initial condition to work with. When you have a differential equation paired with an initial condition like we have here, then this is what's called an initial value problem, or an IVP. So what we're doing in this example is we want to show that the function y equals 5e to the 2x plus x is a solution to this IVP. dy dx minus 2y equals 1 minus 2x. There's the differential equation. And then y of 0 equals 5. This is the initial condition. What this is basically telling me is that if I had my function, if I knew what my solution was and I graphed it, the point 0.04 or 0.5 would be on that graph. So I know 1 point on that curve. Okay, well, how do we show that this is a solution to this? I need to verify that both of these things work with this function. So we've seen how to verify if this is a solution to a dE. I need dy dx for this one. And for this function, dy dx would look like 10 e to the 2x plus 1. Okay? So now let's use this in our actual differential equation. So I have dy dx minus 2y, which is equal to, here's dy dx, 10e to the 2x plus 1 minus 2y. Well, minus 2 times this, because this is what y is equal to, 5e to the 2x plus x. Okay? This is 10e to the 2x plus 1. Distribute the negative 2 in, minus 10e to the 2x minus 2x. I get cancellation here and here, and I'm left with 1 minus 2x, which is exactly what we were looking for right here. Now I need to make sure that my initial condition is also satisfied by this function. So y of 0 is whatever I get from plugging 0 in for the x there. 5e to the 2 times 0 plus x, which also is 0. Okay? That is just 0. 5e to the 0 power is just 5. That also satisfies the initial condition because that's what we needed to get. We needed to get a 5 out of this. Okay, so that's going to wrap things up for 9.1.